Imagine you're at a party and the conversation turns to the future. Someone starts talking about AI, about how it's going to solve everything. They're full of this bright, almost naive optimism. They talk about curing diseases, writing poetry, ushering in a new age of leisure. It's a beautiful vision. You can see it in their eyes. They truly believe we're on the cusp of a utopia, powered by intelligence. Then you ask the simple question, where will the power come from? And just like that, the energy in the room shifts. The utopian vision stutters. They might mumble something about solar panels or wind farms, but the certainty is gone. The grand, shimmering future they just painted suddenly looks fragile, like a magnificent sandcastle built right at the tide line. It's built on a foundation they haven't even considered. Because here's the brutal, silent truth no one at that party wants to say out loud. Every single one of those AI-generated poems, every simulated drug discovery, every answer from a chatbot, it's not made of magic, it's made of jewels. Physical, tangible energy converted into computation. And right now, our entire plan for this intelligence explosion is to power it by begging photons from a distant star and hoping the wind blows. That disconnect between the staggering ambition of our silicon dreams and the pathetic, primitive reality of our energy infrastructure isn't just an engineering problem. It's a form of collective delusion. We are trying to build a cathedral with toothpicks. The mission for this deep dive is to unpack this disconnect. We're going to quantify the staggering energy demand, identify the one technology that seems designed to meet it, these small modular reactors, or SMRs, and really examine the ideological and institutional forces fighting over how fast we should build this foundation.
Right. And the core challenge you face here is realizing that technological progress, especially something as ambitious as AI, is just inseparable from energy supply. This vision of an AI-powered future, driven by philosophies like effective accelerationism, right now it's an empty promise. It's built on a totally inadequate infrastructure plan. So we have to look at the technical solution, just the sheer scale of the opportunity. Then there's the radical ideology that's driving all this demand. And finally, the strategic failure that's preventing the whole system from actually moving forward. We need to understand not just what we have to build, but why we haven't built it yet.
Okay, let's start there. Let's unpack this with the numbers to really grasp the scale we're talking about. This isn't just about plugging in a few more servers.
No, not at all.
We're talking about a civilization-defining energy requirement. Forget consumer demand for a minute. Forget residential electrification. Let's focus just on the industrial sectors. So the heavy manufacturers, synthetic fuel producers, the chemical industry, and critically, the data centers for big tech across North America and Europe. The analysis that we've seen shows that just 11 of these key sectors are projected to hit 17,000 terawatt hours annually by 2050.
17,000. It's an enormous, almost incomprehensible number.
It really is. It's an unprecedented need.
And that industrial need, that 17,000 TWH demand, that's what establishes the market opportunity. It's so important to frame the theoretical upper bound of the solution space right now before we even get into the tech itself. And the analysis confirms that small modular reactors are a very strong technical match for this. Of that total demand, SMRs could theoretically supply up about 15,000 TWH of it.
15,000. Okay, so what does that translate to in like gigawatts of capacity?
In electrical capacity terms, that comes out to roughly 2,200 gigawatts of SMRs. That's what you'd need to meet that technical potential.
2,200 gigawatts. Okay, let's just pause on that number. To put that in perspective for you, that is almost double the current total global operating nuclear capacity.
That's right. The whole world's nuclear fleet today is around 400 GW.
Wow. So we are literally talking about building an entirely new nuclear-powered civilization just to feed industry.
We are. And that 2,200 GW, that's the theoretical market ceiling. This number alone shows you why we can't just tweak the existing energy system. This isn't about a few more solar panels.
No.
We need a fundamental shift. The sheer volume dictates a mass-manufactured, a highly dense, and a supremely reliable solution.
So that brings us to the why. Why SMR specifically? Why do the traditional sources, I'm talking old school, large nuclear plants, natural gas, even renewables, why do they fall short for what an industrial user needs? Especially one that's obsessed with AI and decarbonization.
Well, the traditional sources, they often lack the right combination of density, reliability, and importantly, thermal output and deployment flexibility. Industrial energy isn't just about keeping the lights on, it's about continuous high-intensity inputs that are part of a complex, expensive process. If you stop the energy flow for even a moment,
you ruin the product.
You ruin the product, and you can damage millions of dollars of equipment.
Okay, let's break down the 4 technical requirements where SMRs seem to have a unique advantage. Let's start with high energy density. I always think of this as a real estate problem.
It is a real estate problem.
These industrial facilities, they're space constrained, a chemical plant, a brownfield site.
Yeah.
You don't have thousands of acres to play with.
Exactly. And that density advantage is decisive. This is where nuclear is just in a league of its own. It offers an exceptionally high power density. We're talking 57,000 megawatt hours per year per acre.
57,000.
Yeah. Now, you contract that with solar. Solar gives you maybe 200 milliwatt hours per year per acre.
200 versus 57,000, that's what, nearly 285 times more efficient?
It's not even a comparable technology from a land use perspective. And for a facility with a tight footprint, that's non-negotiable.
Right.
Think about a chemical complex that has to decarbonize. They can't just shut down production, level their site, and spend 5 years building a solar farm. They need a power source you can basically drop into a corner of their lot.
And the newer SMR designs are even denser, right?
Yeah, they are. Some of the advanced designs are 2 to 3 times denser than even traditional light water reactors, which just maximizes that space efficiency even more. It's critical for, small island grids or remote mining operations.
Okay, requirement number 2, extreme reliability. This is where the cost of failure is just astronomical. If you're running, say, an aluminum smelter, you need what? 500 to 1,000 megawatts constantly?
Constantly. Reliability is a core business requirement, not a preference. Nuclear is baseload. It's weather independent, and it hits capacity factors over 90%.
90%. Compared to what for renewables?
25 to 35% on a good day. Now think about that aluminum smelter. If the power fails, the molten metal solidifies in the pots.
Oh, that sounds bad.
It's a catastrophe.
Okay.
It doesn't just cost you the lost electricity. It's millions in physical damage. It can take a week or more to restart production.
And this is exactly why the AI and data center world is watching so closely. Their standard is 5 nines of uptime, 99.999%.
Precisely. Less than 5 minutes of unplanned downtime per year. For these new GW-scale data centers, continuous supply is everything.
So batteries aren't the answer.
I mean, just think about it. If you tried to cover a 1 gigawatt data center's load for just a 4-hour outage with lithium-ion batteries, you'd need over 1,000 large-scale battery systems. The cost would be well over $1 billion.
It's just not feasible.
It's impossible. SMRs bypass that impossible storage problem by just providing the power continuously.
Okay, so that brings us to the 3rd technical requirement, cogeneration potential. This is about efficiency, right? Getting more than just electricity.
Exactly. Getting the most useful output from the reactor. Industry often needs both electricity and heat.
And SMRs can provide both at the same time.
At the same time. It's a process called cogeneration, or CHP combined heat and power. And this dramatically boosts the overall system efficiency to often above 80%.
80%? Compared to what for a normal power plant?
35 to 40% for an electricity-only system.
Wow.
So this massive boost in efficiency improves the whole commercial case. It can potentially reduce the final cost of the SMR's energy by up to 40% for the industrial partner. That's a huge advantage for chemicals, food processing, district energy.
And finally, number 4, high-temperature processed heat. This feels like the key to decarbonizing heavy industry, the really tough stuff.
It is absolutely critical. Traditional light water reactors, they can only give you heat up to about 285 degrees Celsius.
Which is fine for steam, I guess.
It's great for steam or low-temp processes, but it's totally insufficient for, say, synthesizing fuels or complex chemical reforming. The advanced SMR designs, the ones that use coolants like molten salts or helium gas instead of water, they can deliver recoverable heat up to 750 degrees Celsius.
And that's the sweet spot for industry.
It is. That meets the thermal needs for about half of the heat demand in the chemical sector, plus oil refining, steel manufacturing, hydrogen production. This is what unlocks the real path to industrial decarbonization.
So technically, SMRs are the perfect tool for this immense industrial challenge. But here's the disconnect. We have a 2,200 GW potential, a 700 GW accessible market. But where are we right now?
Right now, we're stuck. Under current deployment trends, what we call the current scenario, we're in this bespoke, custom-built construction model.
Every reactor is a unique one-off project.
It's a craft project. And that makes it slow, complex, incredibly expensive, and it carries immense risk. The result is electricity that costs around $125 per MWh and build times of 10 years or more.
And at that price and that speed.
At this pace, we project only about 7 GW will get built by 2050 across North America and Europe. 7.
7 gigawatts. That's That's nothing. It's a rounding error compared to the need.
It's strikingly insufficient. It's a negligible market penetration. It doesn't solve the climate problem or the AI problem.
That 7 GW figure really highlights the structural failure we're talking about. So what's the path? How do we get from 7 GW to unlocking that full 700 GW accessible market? That's a $500 billion to a $1.5 trillion opportunity?
It is. And the answer is moving from custom construction to mass manufacturing. It's about manufacturing innovation, moving from the construction site to the factory floor.
From a project to a product.
Exactly. From a craft project to a standardized product. We see this happening across 3 major scenarios, each one a step change in approach.
Okay, what's the first step?
The first is the programmatic scenario. This gets us to about 120 GW by 2050, so moderate growth.
And that's achieved through what? Better project management?
Primarily through standardization, strong government financing, and better project management practices, yes. But because these are still largely built on site, the costs stay pretty high, around $90 to $125 per MWOCHs, and delivery is still 5 to 7 years.
Still too slow for AI.
Way too slow for the pace of AI infrastructure build-out.
Okay, so the next phase sounds like the real inflection point, the breakout scenario. You're aiming for 347 GW here, and you mentioned it hinges on shipyard manufacturing. What does that mean, building a reactor in a shipyard?
This is the critical shift from building to assembling. The breakout scenario leverages existing heavy industrial capabilities. I'm talking about the same world-class expertise used to build nuclear submarines and aircraft carriers.
So these places already know how to work with nuclear-grade materials and complex systems.
They're accustomed to high-precision welding, intense quality control, fabricating massive, complex components, all in a controlled factory environment. They can mass-produce standardized reactor modules.
And that's what brings the cost and time down.
Dramatically. This approach drops costs into the $60 to $90 per MWH range, and it shortens delivery timelines to just 2 to 3 years.
2 to 3 years, that's a different world.
It is. An average nuclear-qualified shipyard could probably crank out 10 to 15 GW of these modules per year. The entire industry shifts from being about construction project management to being about supply chain management.
And the final goal, the transformation scenario, is where we hit the full 700 GW. That has to be a full-on factory floor.
That's full mass manufacturing. And it means we have to fully embrace something called design for manufacturing and assembly, or DFMA.
Okay, explain DSMA.
It's a total mindset shift. DFMA means the entire nuclear ecosystem is re-engineered around the product, not the construction site. We start treating a 300 mW SMR module not as a unique piece of infrastructure, but as a standardized, repeatable industrial product, like a Boeing 787 or a high-capacity server rack.
So you're stamping them out.
You're stamping them out. We're talking about producing something like 2,300 of these reactors by 2050. This means you need product-based licensing instead of site-by-site approvals. You need factory assembly lines delivering complete nuclear modules and deployment timelines that are measured in months, not years.
And that scale is what finally crushes the cost.
That's what pushes costs down into that highly competitive range of $40 to $60 per MWH. That makes nuclear competitive with natural gas. And, crucially, it allows for the rapid, predictable deployment that the AI economy is demanding.
Let's ground this in the real world. Where is this 700 GW actually going to go? Which industries make up the bulk of this market?
We've identified 5 key sectors. They all converge around 2 things: extreme energy needs, and just as important, inescapable pressure to decarbonize.
And the biggest long-term opportunity at a staggering 203 GW is synthetic aviation fuels.
It's the hard-to-abate sector par excellence. Aviation needs carbon-neutral drop-in fuels, basically synthetic kerosene, that work with the planes and airports we already have.
Because batteries just aren't going to work for a 747.
The physics just doesn't work. Batteries are too heavy for long-haul flights. So producing these synthetic fuels requires enormous amounts of clean electricity to make hydrogen through electrolysis, which you then combine with captured carbon.
And that process has to run 247.
It's a 247 industrial process. SMRs provide the massive, continuous, low-cost baseload power you need, and this demand is going to accelerate massively after 2035 as regulations, especially in Europe, really tighten the screws on fossil-based jet fuel.
Okay, second on the list is coal repowering at 110 GW. This seems like a really pragmatic, smart solution. It's not just about energy.
It's a community solution, and it's probably the lowest hanging fruit for near-term deployment. Existing coal plant sites, they already have the three most valuable, expensive, and time-consuming assets.
Ever.
Grid connections, cooling water infrastructure, and maybe most importantly, a trained local workforce.
Right.
If you can reuse that existing infrastructure, you can cut the investment cost for an SMR by up to 35%.
That's huge. And you're preserving jobs and local economies.
You're providing immediate substantial decarbonization, you're maintaining grid stability, and you're preserving local employment. It's a very attractive path for the first movers in this space.
Next up, the one that's driving this whole conversation right now, data centers. 75 GW of demand. This is the AI nexus. This is where that idea of sovereign compute clusters comes in.
It's a perfect market match for SMRs data centers. Driven by this exponential AI compute need, they demand reliability that exceeds 99.99%. And we are seeing major tech firms and even nation-states starting to prioritize building fully autonomous, nuclear-powered sovereign compute clusters.
Why sovereign? Why not just plug into the grid like everyone else?
Because the grid we have now is often unstable, it's geographically constrained, it's centralized.
Yeah.
It's a single point of failure.
And these new AI factories, they need power yesterday.
They need it now, and they need it guaranteed. They're already willing to pay a premium for it, often over $100 per MWh, which is way above the average wholesale rate.
So they're natural early adopters.
Yeah, they are. The concentrated energy demand, the rapid growth, they're willing to invest directly in the power source. We're already seeing tech companies like Amazon and Google signing initial agreements for SMR deployment. That's a huge early indicator.
Okay, we also have synthetic maritime fuels at 90 GW.
Right. The shipping industry is under intense pressure from the International Maritime Organization, the IMO, to hit net zero by 2050.
So they're in the same boat as aviation, so to speak.
They are. It means a rapid switch to low-carbon ammonia or methanol, often produced right at major port facilities. And while you could put a reactor on a ship, the U.S. Navy has a huge nuclear fleet.
The regulatory hurdles for civilians would be massive.
Exactly. The synthetic fuel route is much easier from a regulatory perspective, and the market size is about 3 times larger. And just like aviation, this demands constant, massive baseload energy to synthesize the fuels.
And finally, the chemical sector at 55 GW, another key near-term market.
The chemical industry is ideal. Their processes are incredibly energy intensive, and they need both electricity and high-temperature heat. A typical plant might need heat up to 750 degrees C for something like steam cracking. SMRs can offer that combined heat and power with incredible efficiency, which is a huge deal for their bottom line.
And they're used to dealing with complex, high-risk operations.
They are. The sector is already highly familiar with complex safety protocols, extensive regulatory compliance. That makes it much easier for them to integrate nuclear technology compared to, say, a brand new data center operator. That familiarity makes them a really strong, immediate opportunity right after data centers.
Okay. We have established the cold, hard, technical need for 700 GW of mass-manufactured nuclear power. Now let's meet the people who are aggressively demanding it. We need to shift from the technical and market reality to the philosophical force that's driving this urgency.
And that urgency is coming from a movement called Effective Accelerationism, or EK. At its core, it's rooted in a really radical techno-optimism. A deep conviction that technological progress has to be the highest civilizational priority, period, regardless of any short-term perceived risks.
So it's a direct philosophical counterpunch to all the caution and safetyism that's been dominating the tech world lately, especially around AI risk.
It is exactly that. AEC is a reaction against what they call decels, decelerationist, and against the caution you see in movements like Effective Altruism, with its focus on mitigating existential AI risk.
For the ATIC crowd, progress isn't a choice.
It's a thermodynamic imperative.
A thermodynamic imperative. Okay, that takes us way beyond just software and economics. What does that actually mean?
It connects back to fundamental physics. They cite people like Jeremy England, who theorize that the universe, just by following the second law of thermodynamics, naturally favors systems that are better at dissipating energy and increasing entropy. So the core belief for Ichue is that life, and especially complex technology, this whole techno-capital machine we're in, is the best way to achieve this cosmic goal, by spreading organization and maximizing energy use.
So the entire purpose of civilization is to, what do they call it? climb the Kardashev gradient.
Exactly. The Kardashev scale measures a civilization's advancement by how much energy it can harness. So to climb the gradient is to maximize energy usage.
Which naturally leads to prioritizing things like advanced nuclear and sovereign compute. It's almost like a thermodynamic currency.
That's a perfect way to put it.
Mhm.
This framework suggests that nation states or tech giants should start measuring progress in joules and energy capacity, not just in fiat currency. It implies that maximizing energy is almost a moral, even a spiritual obligation to the universe's purpose.
And if progress is a universal mandate, that would explain their very aggressive stance against regulation. They just see it as a roadblock.
A huge roadblock. They see heavy-handed regulation as regulatory capture. Basically, rules written by the big incumbent players to protect their own monopolies and crush innovative competition. They argue that this safetyism just cripples acceleration and our global competitiveness. And you really see this in their liability thesis.
Right. So how does each propose managing the very real risks of unrestricted AI development, if not through top-down government rules?
They argue that the market, through liability, will handle risk far more efficiently than any bureaucracy could. The idea is if you deploy a system, especially in AI, you are legally and financially liable for what it does.
So the incentive is to only ship products that are safe and reliable.
Precisely. Customers and organizations will only buy AI products that are proven to be reliable because nobody wants the financial, legal, or reputational fallout from a dangerous product. The market will naturally select for safety.
But wait, history is full of examples where liability only kicks in after a catastrophe, after the damage is already done. What about an AI failure state that could be unrecoverable?
That's the crucial counterpoint. And their answer isn't that liability eliminates all risk, but that it forces efficiency into risk mitigation. They would argue that these arbitrary top-down rules, like forcing every AI lab to spend, say, 30% of its R&D budget on safety, are just inefficient.
Why?
Because it's an arbitrary number. The liability framework forces the market to allocate exactly the right amount of safety budget needed to satisfy insurers and customers. They believe centralized mandates just create bottlenecks and slow everything down.
It sounds like a really radical trust in decentralized decision-making.
Right.
And a fear of centralized power.
A profound distrust of it. They see it as structurally fragile and a systemic risk in itself. It's a single point of failure. A government-backed AI cartel could exert absolute control if it gets a monopoly. The goal is to maintain a kind of fault-tolerant progress that can't be stopped by one single entity.
Fault tolerance, that's an engineering term. How are they applying that to politics and technology?
They use the analogy of quantum error correction. In quantum computing, information is incredibly fragile. To protect it, you encode it across multiple physical locations. So if one bit gets corrupted by noise, the other redundant copies can correct the error.
Okay, so how does that translate to civilization?
If all your power, your technology, your knowledge is concentrated in a top-down hierarchy, well, corrupting a few key nodes can bring the whole system down. They argue that human beings fluctuate. They can be bought out, they can be swayed.
So the recent turmoil at some of the big AI labs, where a small board tried to derail the whole organization.
That's a perfect real-world example of this fragility. Centralized control creates a massive, attractive target for malicious actors or government overreach.
So if centralization is the threat, then the solution has to be total democratization of access.
Exactly. The solution is decentralization and variance. It means open sourcing AI models. It means technological adaptability. It's about ensuring every single person, every hacker, every grad student, every kid in their mom's basement has access to these systems and can contribute to the collective search algorithm of research.
To avoid a winner-take-all scenario.
Right, to maintain a near equilibrium of capabilities so that one market leader can't just run away with the technology and capture the future.
And that thinking extends to the very term we use for this intelligence. They reject AGI, artificial general intelligence.
They reject it as being inherently anthropocentric. It uses human intelligence as the ceiling, as the anchor point.
But isn't that the goal, to create something as smart as a human?
Not for them. They believe human intelligence, which comes from messy biological hardware, is just one tiny point in a vast space of potential intelligences. The real goal is to explore non-biological intelligence, quantum forms of intelligence, things inspired by fundamental physics that no human brain could ever represent or fully comprehend.
That's a truly humbling thought. It's like the shift from believing the sun revolves around the Earth, letting go of our own intellectual centrality.
It's a radical cognitive shift. They argue that by letting go of this human-centric anchor, we can explore a much wider, much larger space of intelligences that will bring massive benefit to civilization. For each day, the choice is ultimately a simple binary: grow or die. They see slowing down the whole degrowth movement as a strategy that just serves our adversaries. And that's what necessitates the immediate, large-scale energy build-out we talked about earlier.
So we have this radical philosophy, effective accelerationism, demanding mass-manufactured cheap nuclear power, that 700 gigajoule transformation scenario, but we're structurally stuck at 7 gigajoule. Why can't the market, which the accelerants trust so much, deliver what they want?
Because the core failure is institutional. It's categorical. We've been using the wrong tool for the job. We have fundamentally misclassified nuclear energy.
How so?
We've tried to manage it as a market commodity when it is fundamentally strategic sovereign infrastructure.
Okay, what's the difference?
It should be treated like a nation's central banking system, or its air traffic control, or its strategic missile defense. These are not things you leave entirely to the whims of the free market.
And you can see the effects of this misclassification in U.S. history, right? This unraveling that started back in the 1970s.
Absolutely. We saw a complete unraveling of coordination once the Cold War urgency faded. In the early days, the Atomic Energy Commission, the AEC, managed everything. It was a single mission-oriented federal body, and they could build things fast. But when that model was dismantled, the government just retreated from its unified sovereign role. You got regulatory fragmentation, new environmental laws like NIPA, and the center of gravity shifted away from the executive branch and into the courts.
Which sounds like a recipe for total paralysis.
It was. It created endless layers of adversarial oversight, litigation, transaction costs, and regulatory uncertainty just skyrocketed.
And we know this was structural, not technical.
We do. There are comparative studies. France had a unified, centralized bureaucracy. They kept their build times around 6 years and built 56 reactors. In the fragmented U.S. system, construction times ballooned from 3 years to an average of 13.
13 years.
And the result was 134 reactor cancellations across the U.S. That was the moment the U.S. nuclear enterprise was paralyzed. It was orphaned by its own structural fragmentation.
So the market frame that we use today is built on a false premise that you can build nuclear using the same decentralized approach you'd use for a solar farm or a gas pipeline.
Precisely. And as long as we keep trying to manage nuclear like a commodity, it will stay frozen. You can throw all the subsidies you want at it, you can tweak regulations, but the structural paralysis remains. We're stuck in a game-theoretic crisis.
A multiplayer coordination failure.
Exactly. Everyone knows the scaled outcome, 700 TeW at 40 millilogens, is the best for everybody.
Yeah.
But no one is willing to move first.
Okay, describe this game-theoretic crisis. You call it a stag hunt.
The stag hunt is a classic model that formalizes this stalemate. Imagine two hunters. They can cooperate to hunt a stag, which is a huge payoff for both. Or they can go off on their own and each hunt a rabbit, which is a small but guaranteed payoff.
So the big prize requires cooperation.
It requires mutual commitment and trust. That's the 700 GW scenario. But the risk-dominant strategy is to defect, to just hunt the rabbit, to wait, because the perceived loss, if you move first and the other guy doesn't, the regulatory exposure, the massive sunk cost, it's just too high.
So everyone waits for everyone else.
Everyone waits. A single developer failing can neutralize everyone else's ambition. The developers wait for guaranteed demand. The fuel suppliers wait for volume orders. The investors wait for regulatory certainty. And the market signals we send, like a new tax credit, they're just too weak. They're reversible. They're temporary.
So because the system is stuck in this state of inertia, no internal signal from the market is strong enough to get everyone to change their expectations and cooperate.
Correct. The problem isn't the scale of the prize. It's the risk of initiation under uncertainty. And this brings us back to why nuclear is different in kind, why it demands federal custodianship.
Right. The 4 characteristics of strategic sovereign infrastructure. Let's run through those again. First, longevity.
First is strategic permanence. Nuclear reactors are expensive up front, but they operate for a century. That kind of capacity anchors your baseload energy across multiple market cycles, multiple elections. It's deep energy security that nothing else can offer. Second is defense alignment. Nuclear energy is not just electricity. It's integral to national security. You have the legacy of the Naval Nuclear Propulsion Program, the potential for SMRs to power military bases, forward operating bases, critical national security compute systems. It's directly linked to the defense industrial base.
The third characteristic gets at the geopolitical risk of the supply chain.
Supply chain sovereignty. The fuel cycle itself is a strategic asset. From 46 to 74, the AEC had full federal control over uranium enrichment and fabrication. In today's world, where fuel supply can be weaponized, sovereign control over that whole cycle, from mining to enrichment to fabrication, is an absolute prerequisite for a scaled national build-out.
And the fourth brings us right back to AI.
Industrial baseload capability. With a capacity factor over 90%, nuclear provides unmatched grid reliability. That's what you need for an industrial revival, for the massive data systems that support AI. You compare that to the 25% capacity factor of solar. It's a different world. It enables the continuous, stable, high-intensity operation you need for steel, chemicals, and these new GW-scale data centers.
So if nuclear is this essential strategic asset, the state doesn't necessarily have to own every reactor, but it absolutely has to set the direction. It has to send a strong, undeniable signal.
It needs to send a credible sovereign signal that is specifically designed to break that multiplayer freeze. And according to strategic communication theory, for a signal to work, to shift everyone's expectations, it has to have three attributes. It has to be visible, irreversible, and costly.
Otherwise, it's just cheap talk.
It's just cheap talk. Visibility means a clear public declaration, but irreversibility and costliness are what really matter.
Okay, so what makes a signal irreversible? How do you make it impossible to retreat?
Irreversibility means you structurally embed consequences that make backing out prohibitively expensive. You enact institutional restructuring, you sign long-term binding contracts, you allocate substantial funds that tie the hands of future administrations.
And costliness.
Costliness means you expend significant political and financial capital that demonstrates true commitment. Unfunded mandates or easily revocable executive orders. They fail this test because everyone knows they're fragile. The only actor that can issue a signal with enough scope and consequence to reset these expectations is the executive branch. It's a direct parallel to Kennedy's 1961 Moonshot Declaration.
That is a very high bar for action. So let's detail this minimum viable sovereign signal, the MVSS agenda. What are the specific structural actions that would convert this stagnant momentum into permanent, coordinated action?
We've identified 4 necessary pillars the executive can initiate right now, acting as that single, credible contracting entity. First, you establish a Nuclear Deployment Command, an NDC, inside the Executive Office of the President.
Why in the White House? Why not just another task force at the Department of Energy?
Because interagency rivalry and fragmentation is the historical cause of failure. The NDC has to be a permanent coordinating body, like a general staff for infrastructure. Its only job is to unify missions, budgets, and schedules across all the fragmented agencies, DOE, DOD, OMB, you name it.
So one person is accountable for delivery.
You centralize accountability at the presidential level, and you force alignment. Everyone is marching to the same drummer. But, and this is crucial, this command structure must preserve the independent safety function of the NRC. The NDC coordinates the build, not the safety regulation.
Okay, Pillar 2 has to address the biggest bottleneck outside of money, siting and licensing.
That's siting and licensing coherence. The executive has to prioritize standardized reactor designs and the reuse of existing industrial sites, especially those retired coal plants. You create a federal brownfield pipeline.
What does that mean?
It means these sites are pre-screened, permits are aligned to a single public timetable, and environmental reviews are accelerated where the infrastructure already exists. Again, this doesn't touch the NRC's independence, but it disciplines all the non-NRC decisions, from the DOD, the EPA, around a common clock. It eliminates years of administrative drift and turns repetition into true repeatability.
Third pillar, supply chain risk. Fuel.
Yes, the Strategic Nuclear Fuel Reserve, or SNFR. This means establishing federal custody of a multi-commodity fuel reserve, natural uranium, LEU, and the ALEU that a lot of advanced reactors need. But the key here is the posture. It has to be contract first, inventory second.
Explain that difference.
The government shouldn't just be hoarding material. It should be offering binding, long-dated offtake contracts for conversion and enrichment services. This is the mechanism that kills supply uncertainty for developers and, more importantly, for their lenders.
Because the government guarantees it will buy the fuel?
When uranium miners and enrichers see a long-term sovereign contract, a guaranteed purchase volume, they will immediately invest the billions needed to build new capacity. When SMR developers see an assured fuel supply for the 60-year life of their plant, their projects suddenly become viable. It transforms the entire fuel cycle from a speculative venture into a strategic constant.
And the final pillar gets right to the heart of the stag hunt. the financial deadlock.
Right. The fourth pillar is creating legible economics via federal power purchase agreements, or PPAs. Multi-decade, non-revocable PPAs issued immediately from mission agencies, like the Department of Defense for its bases, or the General Services Administration for federal buildings. They become the anchor customers.
And how does that break the stag hunt?
This is the single clearest executive lever. It's visible, it's costly, and it's irreversible. These long-term contracts instantly transform speculative high-risk ventures into bankable assets for private investors. A 20-year federal PPA guarantees revenue at a fixed rate, which allows developers to get their construction loans. This sovereign commitment then sets the floor for the market to deliver the scale and the execution.
So we've journeyed from this breathtaking scale, the 17,000 TWh energy challenge for AI, to the radical ideology of effective accelerationism that's demanding it, and finally to this fundamental institutional deadlock, the multiplayer freeze, that makes the 700 GW SMR opportunity seem so out of reach. The path to manufacturing is clear, but the political will to send that coordinating signal, that's what's missing.
And that's why the civilizational challenge of the coming decades isn't one of invention. The technology is here. The urgent need is here. The challenge is structural. It's a choice between doctrine over drift. If we stick with the market frame, we are choosing structural stasis. Capital, talent, and time will just be consumed for minimal gain in endless pilot projects. The only way to unlock that cathedral of silicon dreams, which demands immense continuous power, is through a clear, credible, and irreversible declaration of national purpose. The sovereign has to set the direction so that the market can finally and decisively execute the build.